Today in the workshop, we'll be taking our final look at the Elegoo Smart Robot Car. We'll learn how the collision avoidance and line following features work. We're on track today for a really great episode, so welcome to the workshop. Hello and welcome to the workshop and to the third and final video on the Elegoo Smart Robot Car. Now, in the first video, I assembled this car, which was kindly provided to me by the good people over at Elegoo. This is a four-wheel car, as you can see. It uses an Arduino Uno as its brain, so to speak. It has a custom shield to connect components to, and it comes with a number of pre-made cables, so there is no soldering or anything involved. So it's a very easy kit to put together and a very good value, if you ask me. For the amount of money, you get quite a few things in this car. In the first video, we just tested the motors to make sure that everything was working. In the second video, we went over the Bluetooth and the infrared remote control functions for the car. And now in this video, we are going to cover the collision avoidance and the line tracking capabilities of the car. Now, as with the previous videos, the sketches that Elegoo have provided are just to get you going. You can use these sketches as the basis for writing your own sketches to control and modify the car in any way that you want to. And this is going to be especially true when you see the collision avoidance sketch. In fact, I had to make a number of modifications to it to get it to work in my environment. So I'll show you that, so if you need to make similar modifications, you can do that. Now, what we're going to do today is we're going to start off with the collision avoidance. I'm going to show you the components involved in collision avoidance. We'll look at the theory behind it, and then we'll do a couple of sketches to test the components and to actually do collision avoidance with the robot car. After that, we'll move on to line tracking, and I'll put a little track down on the ground, and we'll watch the car and watch its line tracking capabilities, which are actually pretty impressive. So let's get going and learn something about collision avoidance. So let's examine the collision avoidance method used in the Elegoo Smart Robot Car. The Elegoo Smart Robot Car employs an ultrasonic sensor to detect obstacles. This sensor is mounted on the shaft of a servo motor, allowing it to scan a full 180 degrees. When the car is moving, the sensor is aimed forward. The software Elegoo provides only scans in three positions: left, right, and dead ahead. Now here's an illustration of how the collision avoidance works. When the car detects an obstacle, it stops. Then it scans in both directions and determines which direction has the longest distance to an obstacle. It then turns and moves in that direction. Now here are the connections of the HCSR04 ultrasonic sensor and SG90 servo motor to the Arduino Uno on the robot car. The VCC on the HCSR04 is connected to the Arduino 5-volt output. The ground on the HCSR04 is connected to the Arduino's ground. The trigger input is connected to the analog pin A5 on the Arduino, and the echo output is connected to analog pin A4. The servo's power supply is connected to the 5-volt line on the Arduino. Its ground is connected to the Arduino ground. And the servo control line is connected to pin 3 of the Arduino's digital I/O. Now, when we first assembled the Elegoo Smart Robot Car, we mounted the ultrasonic sensor onto a bracket, which is in turn mounted onto the servo motor. You can see that assembly right up over here. Now, when we did that, we didn't really have a method of aligning it correctly. We just mounted it so it was facing forward, and of course, as we've used the car, we've probably noticed that the servo has moved to one side or the other. Well, now that we want to do collision avoidance, we have to be absolutely certain that the servo is aligned correctly, so that at the 90-degree position of the servo, the ultrasonic sensor is facing directly forward. In order to do that, we're going to run a very simple sketch, and I mean really simple sketch, and all the sketch is going to do is it's going to set the servo motor to the 90-degree position. We can then unmount the ultrasonic sensor and remount it so it is facing exactly forward. And so, without further ado, let us go and take a look at this very simple servo test sketch. Well, I told you this was a simple sketch, and here it is. Now, the sketch uses the servo library. Now, in the Elegoo manual, they state that you might need to install the servo library by going into your library manager, looking for it, and then including it as part of your IDE. In actual fact, the servo library should have been included with the default installation of the Arduino IDE, so you likely don't need to go through that step. The sketch starts by including the servo library and defining a servo object, which they call myServo. And in the setup, we attach the servo to pin 3 of the Arduino, because that's where the control line of the servo motor is attached. And then we write to the servo and send it to the 90-degree position. And that's basically it. There's nothing in the loop. Everything happens in the setup. So the sketch will move the servo motor into the 90-degree position, and we can then use that to align our ultrasonic sensor assembly. Now, I've loaded up the servo debug sketch onto the robot car. The car's not powered up right now. The first thing you want to do before you power it up and run the sketch is remove the ultrasonic sensor assembly. So take the cable off the back and take a small Phillips screwdriver and undo the screw, and then just pry this off and put it down for a second. Now we can power the car up, and you might want to hit the reset button just to make certain that the sensor is in the correct position. And now, with the servo motor centered, place this back on as forward as you can get. And tighten the screw. And now reset it again, just to make certain that it hasn't moved. And that should align the sensor assembly correctly. So now you can turn off the power and put the cable back on. Alright, now that we've aligned our servo motor and ultrasonic assembly, it's time to run the collision avoidance sketch. Now, as I mentioned at the beginning of the video, I made a few modifications to this sketch to get it to work, and I think it could actually use a few modifications beyond that. Now, I modified this for my environment, and it's very important to realize that this is why I did this. One modification I did was one that I did in the previous video with the remote controls. I modified the functions that turn the car left and right to make the motor spin faster. And that may indeed be because of my environment. I'm running this on carpet. If you're running on linoleum or on hardwood flooring, you might find you didn't need to do that. The same goes for what I had to do to the distances on the collision avoidance. I had to set mine back a little further than the sketch showed, just because I found I was getting too close to an obstacle before the car would would stop. Now, again, this might have to do with my environment. I have a very small area to test this car in, and in a larger area, this probably wouldn't have made a difference, and I could have left the values as they were. So with that, I'm going to show you the collision avoidance sketch, and I'll also show you the lines that I modified, and then after I show you that, we will of course give the car a test and have it run around the workshop and try to avoid hitting things. Now here's the obstacle avoidance car sketch that Elegoo has provided for doing what else? Obstacle avoidance. It's a fairly simple obstacle avoidance sketch, but once you understand how it works, you can improve it and fine-tune it so that your car will drive even better. Now we start off by including the servo library like we did in the Servo Test sketch we looked at earlier, and then we define an object called myServo. Over here we define the pins for the ultrasonic sensor, the echo and trigger pins. Now remember, these are connected to analog pins A4 and A5, even though they are digital inputs and outputs. You can use the analog pins as digital pins on an Arduino Uno if you run out of digital pins, and that's exactly what they've done over here. Now these definitions are all for the L298N motor controller, the 2 enable lines and the 4 input lines, and I'm sure you're pretty familiar with this by now, as pretty well every sketch we've used has used these pins. Next, there's a definition for car speed, which they use for all 4 directions, back, forward, left, and right in this sketch. Now, in my case, I found that I needed to increase the value to 220 because 220 allowed my car to move left and right correctly. At 150, I was having some difficulty going left and going right, but it may indeed have been the carpet that I'm using, and so you might want to experiment with this value if you find you have a similar problem. Now, we define 3 integers, right distance, left distance, and middle distance, and I think by their names, their function is obvious. They represent the distance we are from the nearest object to the right, the left, and in the middle, and we initialize these with a value of 0. Next, we go through the 4 functions to make the car directions: forward, back, left, and right. And we've seen these functions before in the other sketches that we've used with this robot car. They essentially just set the enable lines using the car speed in this case. So the enable lines are using pulse width modulation to control the speed. And then the input lines are set accordingly in order to move the motors forward, in order to move them backwards, or to move them in opposite directions to make the car go left or right. Each one of these functions will also print out to the serial port. So if you happen to have a very long USB cable connected to the car while you're running the sketch, you can attach it to the serial port and monitor everything on your computer. But otherwise, you probably won't be making use of these lines. Now we have the stop function, which simply sets the enable lines low so that the car has stopped and the motors are turned off. Now this function over here, distance test, as you might imagine, does a test to see what the distance is, and this is what drives the ultrasonic sensor. Now, we drive it manually with these lines over here, so we create a pulse on the trigger by setting it low, delaying for 2 microseconds, sending it high, delaying for 20 microseconds, and sending it low again. That pulse causes the ultrasonic sensor to send out an ultrasonic pulse, and then we wait and listen on the echo line for that to go high in order to find out how much the distance is, and that's what we do over here. We call the float called F distance, and we use the pulse in command in order to measure the echo pin and see when it goes high, and that measurement determines how far away we are from the nearest object. Now over here we divide F distance by 58, and that will give us the result in centimeters. And then we return the F distance as part of the function. So when you call distance test, it will trigger the ultrasonic unit and report back the distance that's being measured. Now in the setup, it's all fairly simple. We attach the servo motor to pin 3 because that's where the control pin for the servo is. The serial port is set up at 9600 baud, so if you are using the serial monitor, that's what you need to set it to. And then we set the pin modes, and with the exception of the echo pin, everything is set to being an output. And then we call the stop function because we want to make sure that when we first start the car up, it is in a stopped position. And now we go in the loop where we actually measure distances and determine which direction to turn the car. We set the servos to a 90-degree position, so they're set forward. We delay for half a second, and then the middle distance value is assigned to distance test. So we call the distance test function and assign it to the middle distance because we've got the sensor facing forward. Now we check. If the middle distance is less than 20, then we better stop because we're about to hit something. And then we delay things for half a second. We move the servo over to the 10-degree position. Now, I find it interesting they didn't choose to move it to the 0-degree position because you're moving the servo right. However, they've chosen to go to 10 degrees, and so I won't argue with them. But if you want, you might want to experiment with that value. Another value that I found I had to experiment with, and a lot of this had to do with my bumping up the speed of the motor speed, is that the 20 suddenly became too low. So I moved it up to 50. I probably could have gone down to 40. So if you do adjust the motor speed, you'll also want to adjust this value as well over here. It's something to keep in mind. At any rate, back to the sketch. Now at this point, our servo is facing right. We delay for a second and we measure the right distance. We delay for half a second and we write the servo to the 90-degree position, send it forward, delay for another second, and then write it to the 180-degree position. Now again, I'm not sure why they just didn't go ahead and do this and eliminate this line, but that was their choice. So now we're at the 180-degree or full left position, and we'll measure the left distance. And we delay for half a second and move our servo motor back to the center position. And there we go through the logic. If the right distance is less than the left distance, then we call the right function. So we move the motor right and we delay for 360 milliseconds. If the right distance is less than the left distance, then we move the motor left and again delay for 360 milliseconds. Otherwise, if the right distance and left distance are less than 20, and already we're in this loop, remember, because our middle distance has been left in 20, then we're stalled in a corner. We need to send the motor and send it to go back. So we'll move backwards and we'll delay for 180. Now these delays will determine how long the motors are going to spin. Now, if none of this evaluates, then we will go forward. And that's what this else is for. Now this else, if you remember, goes to the very top of this loop over here. That's if the middle distance is greater than 20, then we just simply move forward. And then the loop repeats itself over again. We keep checking the distances and determine which direction to drive our car in. So now that we've seen this, let's actually go and take a look at it in action. I'll put the car down on the floor and we'll give it a try. So now that we've seen the collision avoidance capabilities of the car, it's time to focus on the line tracking or line following capabilities. Now, line tracking or line following is a very common robotics application. It has a lot of practical uses. When you're making a vehicle that has to go along the same path all of the time, this is the easiest way of doing it. It's a lot less expensive and inconvenient than laying down a track for a train type of a vehicle, and it's certainly a lot easier to do than adding algorithms and things for it to recognize its environment and memorize a path. Line following simply follows a line that is drawn on the ground. Now, generally the line is a black line on a white surface, but you can do the opposite, a white line on a black surface. As long as there's enough of a color contrast, it will work. Now, in the Elegoo Smart Robot Car, we mounted a sensor at the bottom, and it actually has 3 infrared sensors on it, and this is what keeps us on track with the line. I'll show you the sensor in a bit more detail in a moment, but before I do, I just want to discuss the theory behind line following and how we're going to accomplish this with this car. Now we'll examine the line tracking method used in the Elegoo Smart Robot Car. The Elegoo car employs light sensors to track a dark line on a bright surface. The tracker device uses 3 infrared source sensor units. The dark line does not reflect light, while the white area surrounding it does. These infrared source sensor units have a digital or high-low output. Now here's the line tracking sensor in detail. It has 3 infrared source sensors, a right, middle, and left one. On the top you'll see a sensitivity adjustment potentiometer. This allows you to fine-tune the sensors. And finally on the bottom is a connector that connects the sensor outputs as well as the power and ground connections for the line tracking device. Here's how the line tracking device is attached to the Arduino Uno on the robot car. The power is connected to the Arduino's 5-volt output. The ground is, of course, connected to the Arduino's ground. The right sensor output is connected to Arduino pin 10. The middle sensor output is connected to Arduino pin 4. And finally, the left sensor output is connected to Arduino digital pin 2. So here's the line following array that is mounted on the bottom of the Elegoo Smart Robot Car. And you'll see on the array it's got 3 optical source sensors. And these devices just send out some infrared light and then they look for it to get reflected back. Now, when a line is in the center, the 2 on the side will reflect back more light than the center one because the black line won't reflect as much light coming back. If, however, the car moves to a position where the line is on one side or the other, then that side will have less light reflected, and the code that we've written will detect that and will adjust the motors and move the car back so that it is getting the line centered again. Now over here you see a small potentiometer, and what this is used for is to adjust the sensitivity of the sensors. Now I didn't find I needed to make any adjustments on it, but if you find you're having difficulty tracking lines, just turn this a bit in one direction or the other and see what the effect is. Now the 3 sensors have their outputs sent out this cable. The cable also carries a power and ground to power all of this, so it's actually a fairly simple device. So we've seen how line following or line tracking works, and we've examined the sensor at the bottom of the robot car. All that is really left to do now is to run the sketch that tracks the line and drives the car around. Now once again Elegoo has provided the sketch to do this, and once again I modified the speed value on it, but it was the only modification I needed to make. I found the sketch worked very well when I put it down on my track. So what we're going to do now is examine that sketch, and then we'll load it up onto the car, and I'll show you my little test track, and we'll put the car on the test track and give it a spin. Now here's the line tracking car sketch that Elegoo has provided in order to do line tracking, and it works with the sensor that we just saw that's mounted underneath the car. Now the sensor, as you recall, consists of 3 light sensors, which should give back either a high or a low depending on whether they see a reflection. Now we defined the 3 sensors over here, the right, the middle, and the left one, and in our definition we do a digital read of them. They're connected to pins 10, 4, and 2 respectively, and the exclamation mark in the front of this is a not digital read, so we invert the value. And so what will happen is if it reflects light back, this inverted value will end up being a low. If it isn't reflecting light back, it'll be high. Now remember, if it isn't reflecting the light back, it means that sensor is positioned right over the black line that we're trying to track. Now next we go through and do the definitions again for the L298N H-bridge motor driver, which we've seen before, and we define car speed. Now once again I chose to bump that up to 220 from the value of 150 they provide, but I urge you to experiment with that value and not just take my word for it. Next we go through the functions that we've seen before to drive the car forward, backwards, left, and right, and in all cases it will print out to the serial monitor. Should you have a very long USB cable connected to the car, you can use your serial monitor to read these as the car moves in different directions. The stop function again is the same. We drive both enable lines on the H-bridge low in order to stop all of the motors. Now in the setup, we set up our serial monitor at 9600 baud, and then we set the pin modes on the 3 different sensors, the right, middle, and the left, to be inputs, because of course we're reading values back from the sensor. Now in the loop, it's actually quite simple. Now the statement here, if LT_M, is valid if it is high. So remember that this is high if it is seeing a black line underneath it, because it's the inverted value from the sensor. So if it goes high, it means we're okay, we just keep going forward. Now if LTR is high instead, we're a little bit too high, so while LTR is like that, we'll move the car right. And we keep doing that while LTR is still high. And then if LTL is high, then we move the car left and keep doing that if LTL is still high. So this serves to call either the right or left function or forward function depending on where the line is, and that will navigate the car on the line. So now that we've seen that, let's go and take a look and put it on a test track and watch it follow a line. So with the line tracking sketch loaded onto the Elegoo Smart Robot Car, it's now time to give it a test. Now in order to do that, I've created something I want to show you. And it's this. Now this may look like a large white sheet of paper with a squiggly black line on it, and that's because it's a large white sheet of paper with a squiggly black line on it. But what it actually is my test track, and the squiggly black line was made using electrical tape. Now for those of you who saw the first episode of this series, you'll notice that in the box that the Elegoo Smart Robot Car came in, there was a roll of electrical tape. And at the time, I had no idea why there was a roll of electrical tape. But it turns out the tape is for doing something like this, making a black line on a light surface. In this case, I used a large white sheet of paper. And I'm going to use this as my test track. The Smart Robot Car should follow this line around the track. So let's put it down on the floor and give it a test. Okay, I'm putting the car on the track. I'll power it up. And it seems to be following the line. It's actually impressive the way it takes the curves. Mind you, I wouldn't want to be a passenger in this car at the moment. It's a rather rough ride. But it appears that the line tracking is working quite well. Alright, well, we've come to the conclusion of this video and to this series on the Elegoo Smart Robot Car, and I think we've covered this thing pretty effectively by now. Now, as always, there is an article accompanying this video, and you will find that on the dronebotworkshop.com website. And when you're on the website, if you haven't already, please subscribe to my newsletter. It's my way of keeping in touch with you and finding out what videos and articles you would like me to create for you. And on the subject of subscribing, if you have not subscribed already to the YouTube channel, please do that. I would really appreciate it. Now, again, I'd like to thank the folks at Elegoo for providing this car for me. It's a great value, so if you don't have a robot car already, you might want to check this out. It comes with everything, including LiPo batteries and a charger, and as we saw with the line following, it even has a roll of electrical tape so you can get started with that. So they really thought of everything with this robot car. It's a very nice design. It would make a great kit for people who are just getting into Arduinos, or for people who want to educate their kids about this. For children, I think this would be a wonderful device. So once again, thank you for joining me here in the workshop, and I hope to see you again very soon. Goodbye for now.